Hi there. So today we're going to be looking at a new section in integration, and that is looking at integrals with infinite domains. Okay, so to start off, I'm just going to do a little picture here. So let's say we had the following function. Okay, it looks something like this. Okay, so this is, for example, 1 over x squared. Okay, it's a rapidly decreasing function. So what we would like to know is if we start at the point x equals 1 and we look at this area all the way out to infinity. Okay, is this area finite or not? Okay, so can we write this total area as a finite number? Or maybe it diverges and the area goes off to infinity. Okay, so that's the question we're asking. In other words, this integral from 1 to infinity of 1 over x squared dx, is this less than infinity? In other words, does this converge? Or does this diverge? And if it does converge, what is its value? Now, as we've written it here, we can't exactly calculate this integral because once we find the antiderivative, how do we substitute in infinity? It's not a number. You can't just substitute it and see what you get. So we need another way of writing out this integral that has the same idea as we want. So instead of writing the integral from, let's say, a to infinity f of x dx, okay, which is problematic because we can't just substitute in infinity. Instead, what we mean is we're taking the limit, for example, as t goes to infinity, the integral from a to t, f of x dx. So instead of substituting infinity directly, instead we write this in terms of t, and then we take the limit as t goes to infinity. Okay, that's the proper way of doing this. We do it with limits. Now, of course, we could do it with the bounds being from minus infinity to something, and we do it in the same sort of way. We have, let's say, the integral from minus infinity to a, f of x dx. Now, again, we can't just substitute minus infinity. That doesn't really mean anything. So what we actually mean is we're taking the limit as t goes to minus infinity, the integral from t to a, f of x dx. Okay, so we have no problem calculating the integral involving t. That's fine. Once we get our answer from that, we can then take the limit and see if the limit converges or not. If the limit does converge, then we say that the integral converges, so we get a finite area. If the limit diverges, then we say that the integral diverges, and so the area goes off to infinity. Okay, so here again, we have the limit, t goes to minus infinity of t. Now, we could get a third situation in which we want the lower bound and the upper bound both going off to infinity. In that case, the integral from minus infinity to infinity, f of x dx, what do we mean by this? Well, what we can do is use the property of the definite integral to split this up into two parts. So we can write this as the integral from minus infinity to a, f of x dx, in which case we can use this second case involving the limit, plus the integral from a to infinity, f of x dx, in which case we're going to use, this first case. Okay, so by appropriately splitting it up into two parts, We can do a limit for the first part. We know how to do that now. We can do a limit for the second part. We know how to do that. We add the results and we get our answer. Now, just a little warning with this part over here. Both of these integrals need to, converge for the resulting integral to converge. If one of them diverges, then the original integral must also diverge. It's like saying infinity plus 2. Okay, that's still going to be infinity. It doesn't matter if one of them converges, we need both of them to converge. Okay, so it's an extra condition if we have this double-sided infinite integral. Okay, so please watch out for this third case over here, where we've got the two infinities to deal with. Okay. So with that in mind, let's take a look at our first example. So example number 1, we have the integral from 1 to infinity of 1 over x squared dx. Now we know that this infinity is just notation. What we really mean is the limit, as we discussed. So we need to write this properly as the limit as t goes to infinity, the integral from 1 to t, 1 over x squared dx. Okay, now this makes sense. We can handle this. So we leave the limit for last. So this is the limit as t goes to infinity of, we can take the antiderivative. Okay, but let's write this first as the integral from 1 to t, x to the minus 2. Okay, so I just want to show all the steps involved. So we can write this as the limit as t goes to infinity of, now this is just the power rule law. We add 1 to the exponent to make it minus 1 and divide by that. So we're going to have minus x to the minus 1 from 1 to t. Okay, so this is going to be the limit as t goes to infinity. If I substitute t, I'm going to get minus 1 over t. Then I'm going to have plus 1 over 1, which is just 1. Now, the limit as t goes to infinity, remember way back when we did the Riemann sums and the Riemann integrals, if we have something in the denominator and t is going to infinity in this case, this is going to go to 0. So that's going to go to 0, and the result is just 1. So we end up with a finite result, which means this integral converges, and we now know that the total area from 1 to infinity is just 1. Okay. Let's take a look at another example. Example 2. We have the integral from 1 to infinity of 1 over x dx. Okay, so similar to what we had before, but now the exponent of x is 1 instead of 2. Okay, does this have an effect? Let's have a look. So what do we mean by this? We mean the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. Okay, that's what we really mean when we say that there's infinity in the upper bound. Okay, so let's do the integral and then take the limit. So we have the limit as t goes to infinity. This is going to become the natural log absolute value of x from 1 to t. This is equal to the limit as t goes to infinity of the natural log of t in absolute values minus the natural log of 1. Okay, but the natural log of 1 is just 0, so that goes away. Now, with the natural log, if t gets bigger and bigger, the natural log also gets bigger and bigger. In fact, it's unbounded. So as t goes to infinity, this natural log also goes to infinity. In other words, the integral diverges. Yeah, it doesn't have any finite value, so we can't assign a value to it. It just goes off to infinity. Okay, and we just say the integral diverges. So you see that with these expressions here, with the 1 over x to some power, it does matter what the exponent is. So in the previous case, we had 1 over x squared. That converged. We got a value of 1. However, in this case, we've got an exponent of 1, and the integral diverges. So again, even if they are similar, you still need to be careful with the integration and then taking the limit. Okay, let's take a look at our third example. So we've got example number 3, the integral from 0 to infinity of x e to the minus x dx. Okay, now again, what do we mean with this upper bound being infinity? Well, we mean we're taking the limit. So we have the limit as t goes to infinity, the integral from 0 to t of x e to the minus x dx. Now notice when we're doing this integral, we have a product of functions. So we're going to have to use integration by parts. So let's do that. We let u be x because that's easy to differentiate. We let dv be e to the minus x dx because that's easy enough to integrate. So du is going to be dx and v is going to be minus e to the minus x. Okay, so what do we get here? We get the limit as t goes to infinity of u times v, so x e to the minus x from 0 to t, minus the integral from 0 to t of v du. So that's minus e to the minus x dx. Okay, so that's after doing our integration by parts. So remember, just because we're doing a new section doesn't mean we're not going to be using all of the stuff that we learned before. So we could be using u substitution, we could be using integration by parts, maybe trig substitution, maybe trig integrals. Okay, all the stuff we learned before, that could appear as well. Maybe partial fractions could come up. So you can't forget what we learned just because of the new section. Okay, so this is going to be the limit as t goes to infinity of, let's substitute in t. So we're going to have t e to the minus t. And if we substitute 0, we're going to get 0. So that's fine. Plus the integral from 0 to t e to the minus x dx. Okay, the minus and the minus just make a plus there. So let's do that integral now. So we have the limit as t goes to infinity of t e to the minus t plus, and now this is going to be minus e to the minus x from 0 to t. Okay, same thing, we just need to substitute in. So this will be the limit as t goes to infinity of t e to the minus t minus e to the minus t. If we substitute in the t, if we substitute the 0, we're going to get minus minus, so it's a plus 1. Okay, because e to the 0 is just 1. Now we need to take the limit as t goes to infinity. Now e to the minus infinity, okay, so we have e to the minus t for larger and larger t values, that's going to go to 0. Okay, because remember, e to the minus very big number gets smaller and smaller. So eventually this is going to go to 0. The limit as t goes to infinity of 1, that's just 1. There's no t dependence there. However, this first term is a bit more tricky. Okay, if we take the limit as t goes to infinity, the first bit is going to go to infinity. The second bit is going to go to 0. So we've got that indeterminate form, right? Remember back in last year, you looked at those L'Hopital's rule with that 0 over 0 or infinity times infinity, those indeterminate forms. Whenever you get an indeterminate form like that, you need to do a little bit more extra work to see what the value actually is. In this case, we've got an infinity times 0 indeterminate form, so we can go ahead and use L'Hopital's rule. So this is going to be the limit as t goes to infinity of, well, we have t over e to the t. Okay, something like infinity over infinity. And then we still have the plus 1. Don't forget about that. Now we're going to use L'Hopital's rule. So this is the limit as t goes to infinity of 1 over e to the t. And again, we've got the plus 1 here. Now e to the t as t goes to infinity, that's going to get larger and larger. So the resulting fraction is going to get smaller and smaller. In other words, this is going to go to 0. Okay, so now we know the true value of this limit. Okay, it did have an indeterminate form first. We use our L'Hopital's rule to figure out what that value is. So finally, we get the value of 1. This is finite, so we can say the integral converges. And we also know that the area is 1. Okay, let's take a look at the last example for today before I give you your homework question. Okay, so we're on example 4. We have the integral from minus infinity to infinity of 1 over 1 plus x squared dx. Okay, we want to try to work this out. Now we've got this double-ended infinity going on. For the lower bound, we have minus infinity. For the upper bound, we have positive infinity. Remember what I said, if you have something like this, we split it up into 2 parts. Okay, so we can write this as the integral from minus infinity to 0, 1 over 1 plus x squared, plus the integral from 0 to infinity of 1 over 1 plus x squared. Now, choosing 0 is a bit arbitrary. You can choose whatever you like. I just chose 0 because that's kind of in the middle. Okay, but you're free to choose that. Okay, so let's take a look at these in 2 parts now. So for the first bit, we're going to be looking at the first integral. So if we write that as a limit, we're going to have the limit as t goes to infinity, t goes to minus infinity, the integral from t to 0, 1 over 1 plus x squared dx. So this is going to be the limit as t goes to minus infinity of, this is going to give us arctan of x, going from 0 at the top, t at the bottom. So this is the limit as t goes to minus infinity. Okay, the arctan of 0, that's 0. And then we have minus the arctan of t, that's just the arctan of t. Okay, so we have minus the limit as t goes to minus infinity, arctan of t. Now, as t goes to minus infinity, the arctan of t goes to minus pi over 2. But we've got this minus in front here, so this is just pi over 2. Okay, so we know that the first part converges. That's good, but that's not all, because we also need the second part to converge. Okay, so we're halfway there. If the second part converges, then we can just add the values to get the total sum. Okay, so let's look at the second part. We know that the second part has an upper bound of infinity, but we know we should write that as a limit. So that's going to be the limit as t goes to infinity, the integral from 0 to t, 1 over 1 plus x squared dx. Okay, now we can do this quite similarly to what we had before. This is going to be the limit as t goes to infinity of, we're going to get arctan, same as before, but now the bounds are going from 0 to t. So we're going to have the limit as t goes to infinity of the arctan of t minus the arctan of 0, but that's just 0, so we don't need to write that. Now, as t goes to infinity, the arctan of t is going to approach pi over 2, which also converges. Okay, it's a finite number, so the integral converges. So the second part converges. So we've got that the first part converges to pi over 2. The second part converges to pi over 2. So we can just add the two parts together. So finally, the integral from minus infinity to infinity, 1 over 1 plus x squared dx is equal to part 1 plus part 2. So that's pi over 2 plus pi over 2. That's just pi. Okay, so maybe it's odd that pi shows up. This we have 1 over 1 plus x squared. There's no real mention of circles anywhere, so why should there be a pi? But we know from the antiderivative being arctan, which is related to the trig functions, we should be getting pi somewhere there. Okay, so that's the answer for that. So whenever you have these double-ended infinite integrals, remember to split it up into two parts. So we can take the limit for the first part, the limit for the second part. We check that both parts converge. If they do, we can add them together to get the final result. If one of the parts diverges, then both parts don't matter. The whole thing diverges. Okay, and remember when we say diverge, we mean it goes off to either positive infinity or negative infinity. Okay, either way, it diverges. Okay, before we go, let's take a look at the homework questions, or just homework question. It's just one today. So homework question. We have the integral from 1 to infinity. Okay, so we know what that means now. 1 over x to the p, where p is some number. The question is, for which values of p does this integral converge? So we already know when p is equal to 2, this converges. We showed that already. When p is equal to 1, we showed that it diverges. So depending on the value of p, this could either converge or diverge. We know that. So what I want to know now is what are the possible ranges of p that give us a convergent value? Okay. Okay, so that's the homework for today. Just one question. Okay, and as always, if you have any questions, please post them on the class WhatsApp group. I can answer them there, or you can send me an email. I can answer you there as well. Remember, the tutors are available. So if I'm busy, you can always ask them for help. Tomorrow, which is the Wednesday, we're going to have the quiz. It's on trig substitution, only on trig substitution. There's 3 questions, 5 marks each, and it's multiple choice. So you do your working and then you can select which is the correct value. Okay, so only 3 questions and you have your full 1.5 hours for the full test time. Okay, so take your time if you need. Okay, and then please remember test 3 is coming up. So please make sure you go over all of the previous work that we've done so that you're ready for test 3. We only have 2 more sections to go through. Improper integrals with discontinuous functions and finding the length of curves. Okay, so 2 small sections to go through and then we're done with the semester. Okay, so not too much. But yeah, if you have any questions, please don't hesitate to ask on the WhatsApp group and do the homework. Okay, so these homework questions are very important to go through. Okay, I'll see you tomorrow in the tutorials. Bye.